Okay, this video lesson deals with another type of application with molar concentration, and that's dealing with stoichiometry with solutions. Okay, so we've looked at stoichiometry in the past. The basis of all stoichiometry is like being a recipe for how the different reactants, how much of each reactant is required to come together to produce varying amounts of products. But the basis is the mole. Okay, so these, if we can read along here, it says these calculations allow us to determine the amounts in moles of reactants needed for a reaction and the amounts of products generated during the reaction. And the base of all these calculations is the mole. So in general, what we've looked at mainly have been solids. Okay, and when we've looked at solids, we've really only used one formula, which is the molar mass formula. It's moles is equal to mass over molar mass. Okay? And that's really all that we can use for solids. I guess there is a situation where we could have the volume of the solid, but we need to know the density. When it comes to liquids, okay, we have to remember liquids as a pure substance is what we're really talking about. We could be dealing with the mass, which has been used before, but we could also be dealing with the volume of the liquid, which is often a little bit easier to determine. But when we have the volume, okay, we're going to need the density of that liquid because we're dealing with a pure substance. It's not a mixture. Okay. Now, when it comes to this unit, we're looking at solutions. We're dealing with mixtures, so we don't need the density. Okay, because that's only for a pure substance. That's going to allow us to figure out the mass of that substance. What we need is the concentration, because the concentration tells us how much of the solute, which is usually the reactant, is present in a given amount of volume. Okay, so we'll use this formula, moles is equal to concentration times volume. So we're not going to use this one. We have to be very careful about that. If we were given the concentration not in moles per liter, but rather in a mass amount, we would be using mass. Okay, so we have to be careful about what we're given. Okay, if it's solute over solution, like a weight per volume amount, okay, we would be able to get the mass by rearranging this formula so that the concentration times the volume, as long as these units are compatible, would give us the mass, more than likely in grams. And don't forget, these ones generally have a multiplier, so we'll have to take that into account as well when we determine the amounts or the mass that we have. Okay, but this is the preferable unit because it gives us moles directly. Okay, in the next unit or the next portion of this unit, we'll be looking at gases, and we will do stoichiometry with gases as well. But there's going to be another formula, and we haven't introduced it yet or learned about it yet. But basically, just to give you a bit of a heads up, this is known as the ideal gas equation, and it basically allows you to figure out the number of moles of the gas, okay, given a couple of its properties, that being pressure, volume, and temperature. And there's a gas constant in there that allows us to relate all these different quantities together. Okay, so just as in the last little section, we're going to model an example. Okay, so we'll look at this first example here. Okay, so the first example, we're dealing with the reaction of zinc and hydrochloric acid to produce zinc chloride and hydrogen gas. Okay, so we got different states of matter, and that's really kind of important to really take note. If it's a pure liquid, we're going to use one of the other formulas, but if it's a mixture, an aqueous mixture, we're going to want to make sure we use the moles is equal to concentration times volume formula. So we really have to be paying attention to what formulas we're using. Okay, so it says 500 milliliters of 0.7 moles per liter solution of HCl reacts with some zinc metal. Okay, so key in on the numbers and their units. Okay, and it says what mass of the zinc chloride are we looking for, and what mass of zinc is needed. Okay, so 2 questions. So we have 2 parts to this. Okay, so let's just fill in organize our stuff within a chart. Okay, so we'll start off with the given information. Okay, so the given is that there's 500 milliliters That's not a good unit. We need it in liters, so we change it to liters by dividing by 1,000. Okay, and the concentration is 0.7 moles per liter, so we're going to use that. Okay, and now we're going to proceed to figure out what the masses are, and that's what we're looking for. Okay, so I know it's already written out here, but I think you understand the idea. We're going to move down the table here by using whatever formula is needed to get moles. So I multiply these two together, okay, because of the formula. Once I find out the moles of HCl that's being used up, then I'm going to move to the other parts using a ratio or proportional reasoning, okay? And we're going to use the numbers in front of the reactants or products in the balanced equation, the stoichiometric coefficients, in order to figure out how many moles are going to be produced. Well, this is 2 to 1, so there's 2 of these for every one, so there's half as many moles being produced of zinc, and there's half as many moles of zinc needed. Okay, so you're dividing. So in by 2, we might use a little bit more of a ratio or another little technique if these are not simple numbers like this. If there's a 2 and a 3, we might use something a little bit different, but in this case, it's pretty straightforward. Okay, so we divide these by 2, okay, and then move up the table. And going up the table, because this is a mass, and we're also looking for the mass here, even though this is a concentration, we are looking for the mass. We're going to use molar mass. So the molar mass of zinc is 65.38, zinc chloride is 136.3, and we're going to multiply. An alternative to this is to actually figure out what the final concentration of zinc chloride would be. And what we could do is we could just take this molar amount and assume that we still have the same volume. We could have divided, and we would have got a molar concentration of the zinc chloride. And it should be half of that because the number of moles has gone down. So it should have been 0.35 moles per liter. That's another type of questions that we could have. Okay, so that's one example. Okay, we could have added another step to figure out how much gas we had if we're given the temperature and the pressure. Okay, or we could have figured out what the pressure is if we knew what the volume and the temperature were. But we haven't looked at ideal gas laws, but that will be next. Okay, so that's just one extra step. It's just applying the right formulas for the right situation. Okay, so here we have a second one. Okay, so a little bit harder question says we have 0.5 moles per liter calcium chloride, 1 mole per liter potassium carbonates, and they're going to react together. What volume of each solution is needed to produce 10 grams of calcium carbonate? Kind of an important kind of idea is we have a goal in mind. We're looking for a certain amount of product. How much of these starting materials do we need? Okay, and in some kind of industrial process, that's what would be calculated, so that it had at least that amount is being produced. Okay, so I'll leave you to take a look at this use the chemical equation and start filling in your chart and organize your information, and then we'll go through it. Okay, so what you should have done is keyed in on our initial information. So 0.5, we know it's 1 mole per liter, and we know that we want 10 grams of calcium carbonate. So that's all our given information. Okay, we're not given the volumes, so that's the question. So that's next. Okay, so what volumes? So if that's the case, we don't know any more information about this. We're going to have to figure it out from the mass of the calcium carbonate that we need. Okay, so sure enough, we'll use our molar mass, find out the number of moles. We know the moles is the basis of all stoichiometry. These are all one-to-one relationships. There's no coefficients needed for any of these. So one-to-one just means the mole amounts are going to be the same. So 1-to-1, we have the mole amounts are both the same. Okay. Now what we're trying to do is figure out the volume. So we need to use this little triangle or rearrange the equation. we have the concentration, we have the moles, we don't know the volume, so covering that up, we know that we have to use the formula in the form moles divided by concentration, so that's why we have it that way. We know what the concentration is, it's 1, so 0.0999, approximately 99.9 or 100 milliliters, or in liters, 0.1 liters of the potassium carbonate. Same idea here as well. This time the concentration is half as much, so we're going to need double the amount. Okay, so that's going to turn out to be about 0.199 liters or 199 milliliters as my final answer. And then just finishing off with therefore statements would be great. Okay. What you can do now is, this is sometimes done as a lab activity. You could also do this for your question if you remember what the solutions are for the copper sulfate. Thank you very much.